Greetings pre-calc students, this is Mrs. D, and this video is called Pre-Calc Homework Help 3.5. For some reason I think it rhymes. Pre-calc Homework Help. Here we go. Our first problem from homework deals with the flu. So there's a model here. Notice it's a logistic model. The function shows the number of people infected with the flu after a certain number of days of initial onset. Just a quick little think about it here. The initial amount of people who have this flu, just so you realize that reaching 100 is not going backwards in time, but the initial number of people with the flu here, if we plug in times 0, is 200 divided by 1 plus 39, or 200 divided by 40. That's a nice number, 5. So 5 people start out having this flu, bummer, and then it spreads. It spreads and it spreads, and we want to know when will there be 100 people with the flu. Seems like it might take a while, but it does kind of change here rather rapidly at the onset. So let's follow this model. And do you see what I'm talking about here? The initial rate of change is rather quick here, and then it levels off to whatever carrying capacity. The population can't exceed a certain number of people having the flu, obviously. So my first step in solving for time here, the question when will be answered with a time number. I'm going to start by multiplying both sides of the equation by that denominator. Now we're equal to 200. You may distribute if you see that, make sense of that. Otherwise you can simply divide here by 100 on both sides. I'm using inverse operations, and that will lead us eventually to a little exponential inverse as well. I will be subtracting 1 next, leaving me with 39 e to the negative 0.3t equals 1. Isolate this exponential bit, and I have 1/39. Now the inverse operation for this exponential is the logarithm in the same base, so we will use natural log on both sides of the equation. That will maintain the equality. And ultimately then I have negative 0.3t equals whatever the natural log of 1/39 is. You'll definitely need your calculator to finish this problem. And then lastly, to solve for time, you'll divide by a negative 0.3. This fraction, natural log of 1/39, should also be a negative number, so when you divide by a negative 0.3, you get the positive time of approximately 12.2 days. Not even 2 weeks and 200 people are infected with the flu. So maybe think about that. Stay home if you're sick. Don't come to school and get us sick. Get healthy. The flu spreads rather quickly. Based on this model, it would take only 12 days to infect 100 people if only 5 people started out as being sick. Our last application here, and yes, we're only doing 2 homework problems, but they're 2 good ones. We are looking at a half-life model, and half-life, recall, is the amount of time that it takes for a substance to decay to half of the initial amount. It's a measure of time, usually in years. This substance, we already know the half-life is 4.9 times 10 to the 7th years. That's a lot of years. If I start writing a model here, an exponential model, I can anticipate my base should be less than 1 because it's exponential decay. More specifically here, maybe the base should be 1/2. That seems right. But I will not use just 1/2 to the time t, because that would mean its half-life is 1 year. Per 1 year, you lose half of the substance. No, that's not right. So actually, it happens every 4.9 times 10 to the 7th years. So that's per 49 billion years. So this model will work. Notice we don't have an initial value given to us. You have 2 options here. You can either choose a number, start with 100, and then you know the half-life takes you to 50. You could start with 8, and half-life brings you to 4. You could start with any number. 72 half-life brings you to 36 grams, so you can work with it that way, but I'm going to be adventurous here and use arbitrary values. So whatever the starting amount is, we're going to decay to 2/5 of that amount. So that will be 2/5 of A. Again, you can choose a number for A if you like. It'll work out to exactly the same step right after this. So this model, as I start to solve, it's going to be okay that we don't know A, because when I divide, I will be left with 2/5. And notice we only have the variable of time left. So if I continue working through the algebra of this solve, I'm trying to figure out the time. I'm going to use logarithms next. Since we don't have any common base here, let's just use log base 10, log, and that will help us, because then I'm going to switch up to decimals. 0.4 is the same as 2/5. That helps us actually over here, because that property of logarithms for powers allows me to bring that power as a multiplier in front. And then it's no longer an exponential type of problem. So my next line of work will be to try to solve for t a little bit further down here. I'll divide by 0.5 that logarithm. Oh, we're getting closer. T over 4.9 times 10 to the 7th will be that quotient of log 0.4 divided by log 0.5. Then I simply need to multiply by this humongous number, 4.9 times 10 to the 7th. 4.9 times 10 to the 7th. I anticipate the amount of time it takes to get to 2/5 should be longer than 4.9 billion years, 49 billion years. Here's a little tip for your calculator. If it were me, I would multiply or divide this first, multiply by the 4.9, and I'm actually going to leave the times 10 to the 7th in my answer. So I'm finding 6.477 times 10 to the 7th years to decay to 40% of the original amount, or 2/5 in other words. If you want a more accurate, or I guess a more sensible answer there, you can multiply by 10 to the 7th power. It's going to be 6,477 and like 4 more zeros. So 64 billion years. No, that's just million, Mrs. D. Still a long time. And notice I kept a few decimals here. That actually keeps a few 100,000 years in the mix, so don't round it too much. That will take quite a bit of time, but eventually it will get down to 2/5 of its original amount, and that's the amount of time that it took. Make sure your answer is reasonable. If you're getting something in the hundreds, something went wrong, or you rounded way too much. Continue problem solving. Be sure to be careful about your setup. All of these problems are doable. I believe in you. Keep thinking.